I'm Xueyan from UC Davis. Today, I would like to present our work, Progressive Temporal Feature Alignment Network for Video Inpainting. This is a joint work with Lin Jie, Liu Ding, and Yang Jie. Video inpainting is a task that aims to fill spatial temporal cropped regions with plausible contents. The input of this task usually consists of cropped video frames and their corresponding masks, and the outputs are the inpainted frames with plausible contents. Here, we show a demo video on object removal, which is an application of video inpainting. Before introducing our approach, we first ask a question: what is critical for video inpainting? Here, we show two demos on image inpainting and video inpainting separately. In comparison with image inpainting approach, video inpainting approach takes multiple frames as input instead of one, and this enables the network to retrieve missing contents from surrounding frames, which contribute to the superior performance of video inpainting. There are three major directions on how to find correspondence from neighbor frames, including attention, optical flow, and 3D convolution. In this paper, we take a combination of the last two directions. The major advantage of the optical flow approach is accurate spatial alignment, but it suffers from preserving the fine-grained structures as the error in flow will accumulate through propagation. In contrast, 3D convolution approach could preserve detailed structure but suffers spatial misalignment. In this paper, we combine 3D convolution with optical flow approach to benefit from their advantages while offsetting their disadvantages. In optical flow approaches, they first compute a cropped optical flow using existing flow prediction method, such as FlowNet2, and then they use the proposed flow completion method to inpaint the cropped optical flow. Finally, the inpainted flows are used to warp pixels from surrounding frames. In 3D convolution approach, the model constitutes of three components, including an encoder, a skip-connected decoder, and a temporal patch gain discriminator. In our approach, we change the unit encoder to ResNet and modify the original ResNet bottleneck block to TSAM bottleneck. For each TSAM bottleneck block, we replace the first conv layer with TSAM conv, which takes the completed flow and frame features as input. The temporal shift and align module is first used to integrate temporal information and align the feature spatially. Then, the output feature is passed to a conv layer and attended with a gating signal. Temporal shift and align module is originated from temporal shift module, where the first F channels are shifted downwards and the second F channels are shifted upwards along the temporal dimension. In this way, temporal information is integrated without the noticeable overhead. However, when exchanging features across frames without any alignment, spatial mismatch occurs as shown in T=I from the above figure. Thus, we propose temporal shift and align module. By warping the feature using completed flow before shifting, the shifted features is well aligned with the target frame. Thus, features at all the timestamps are well aligned with each other. Here, we show a qualitative results on various mask types. Our approach could inpaint the missing region with accurate and temporal consistent content. We observe that FGVC will suffer on fine-grained structure details occasionally, and SCTN will predict blurry results in some cases. Please scan the QR code for the full version of the video. As shown in this table, by combining 3D convolution and optical flow approach, our method outperforms its counterparts as FVI and FGVC, which indicates the proposed temporal feature align module is critical to improve the visual quality of the inpainted videos, especially improve the spatial alignment upon 3D convolution approach. Here, we ablate TSM module compared with TSAM module. The second and third row indicate that using both predicted flow and ground truth flow will improve the performance upon baseline, and this indicates that it is effective to use TSAM module to align the features spatially. We claim the following contributions. We propose a novel temporal shift and align module that artfully combines 3D convolution and optical flow approach. Extensive experiments demonstrate superior performance to existing video inpainting methods in terms of structure preserving and temporal coherence. Thank you for listening.